So moving on to elastic collisions, you might think, based on this idea of conservation of momentum, because momentum depends on two quantities, mass and velocity, you might think that it follows from that that kinetic energy is also conserved because kinetic energy also depends on mass and velocity. But it turns out that that's only true in very specific sets of circumstances. So let's look at a relatively basic example of a scenario where kinetic energy is not conserved. So let's say that we have a soccer player, okay, and the soccer player is running towards a ball. He's running. There's our soccer ball. And what our soccer player doesn't know is that the ball is covered in some kind of invisible sticky substance. So when he goes to kick the ball, instead of the ball moving, the ball just sticks to his foot, and he's, he's very confused. Here he is with the ball sort of just stuck to his foot. Okay, but he keeps moving. Okay, so he has some initial velocity. Let's say he's running at 5 meters per second, and let's say that the mass of this soccer player is maybe 60 kilograms, and the mass of the ball, let's say it's half a kilogram, just for simplicity. Okay, so the soccer player is going to keep moving. Okay, it's going to have some new velocity. We'll call that v prime. Okay, this prime mark is used very often in momentum problems, so get used to that. So in our first scenario where the person has yet to kick the ball, our person is the only thing that's moving. Okay, so the initial momentum is going to just be the mass times that initial velocity. Okay. In the second scenario, the person and the ball have sort of stuck together. Okay, so they become one mass, and they're going to move with this new velocity v prime. Okay, so p final, okay, is going to be m1 plus m2 times v prime. Okay, but what we know is that these two momenta are going to be equal to each other, okay, because the momentum is conserved. So if we want to know what the new velocity is, that's relatively simple to calculate. We just do m1 v naught equals m1 plus m2 times v prime. Okay, oops, put the prime mark here. Okay, and so then it just becomes a matter of division. Okay, so we do 60 times 5, and then we divide by basically 60.5. Okay, and we get that v prime. If we plug that in on a calculator here, we'll do 60 times 5, and then we'll divide by 60.5. Okay, and we get about, let's call it 4.96. Okay, so v prime is 4.96 meters per second. Okay, so it makes sense. After our soccer player kicks the ball and the ball sticks, they keep moving together, but they move a little bit more slowly than the soccer player was moving initially. So we might then want to compare the initial and the final kinetic energy. So if we look at the initial kinetic energy, K naught, that's just going to be 1/2 m1 v naught squared. Then if we look at the final kinetic energy, okay, that's going to be 1/2, and now it's going to be m1 plus m2 and then v prime squared. Okay. So again, you might think on a somewhat intuitive level that these should be equal, but let's just see. So if we run the initial kinetic energy, we'll do 0.5 times 60 times, and then our initial speed was 5, so we'll do 5 squared, so 25. And so we get a nice, neat, round 750 joules of initial kinetic energy, okay? But if we run the numbers with our final kinetic energy, we'll do 0.5 times 60.5 times, and then we'll do that 4.96 squared, okay? And we get only about 744, let's call it 0.2 joules. Okay, so you can see we've lost, just about 6 joules of energy. Okay, it's not a huge amount of energy, but it's significant. And so you might wonder why and where that energy went. And that energy goes to non-conservative forces. Okay, so when you have a collision like this, there's going to be sound as the person kicks the ball. There's going to be heat exchange. And so all those factors turn into, a small but still noticeable discrepancy in initial and final kinetic energy. So in any type of collision, if you make your system big enough, momentum is conserved, but kinetic energy is not conserved.